Alright, I'm just gonna start. This is worksheet 2. This might be a bit longer, so I'll add like the timestamp, so hopefully it's not like too long and you can skip to the part you like. Let's just start off with this first one. So we have this graph for displacement. I forgot to add this displacement versus time, and we just got to figure out the direction of the acceleration, the direction of the velocity, direction of the displacement, and then the direction of the F net. So, for each of these points, so let's just start off with the point A. The displacement is in the positive side, so we can just write positive. And because it's in the positive side, the F net is going to be negative, and then if the F net is negative, the acceleration is negative. So, just remember, the restoring force is like the force spring. So, if I go more positive from the equilibrium, the force is going to point in the opposite direction. So in this case, it's negative, therefore acceleration is negative. To figure out velocity, I would just look at the tangent line, right? Like at this point, the slope is 0, so the velocity will also be 0. And we can really just use that thinking for all the points. Once again, point B, positive displacement, has to have a negative F net, so a negative acceleration, and now the velocity is a bit more, the slope at least is a bit more negative. Okay? So, the displacement at point C is 0, so the F net is 0, and therefore the acceleration is 0, and then we know our velocity is still pointing in the negative direction. In fact, we can see the velocity is negative up until point E, where E is 0. I hope those are the right letters. Yes. So for velocity, I can just, oh, did I do D? Oh, I did them all wrong, my fault. A should be this, and then this should be 0, and then this should be this. Okay, my fault. So, yeah, point C should have the 0 acceleration, 0 displacement, all that good stuff. Hopefully that didn't catch you guys off. So, but still, for point D, for points D3, we can draw the velocity as negative, and then at E, it's going to be 0. So, at D, and I'll fix these, D is, okay, so now, for the D section, the displacement's negative. Okay, I'm making this way too long, but the idea is that negative displacement, you're going to have a positive net force and a positive acceleration, but still that negative velocity. And for point E, yeah, same thinking. Now it's going to have, once again, negative displacement, positive force, 0 velocity. So try F through G through H on your own. I'm just going to quickly do it here, and then you can check your answers. So let me just, I think we're going to have, okay, so this is what I had for F through H. So the acceleration and the net force are positive, the displacement is negative, and our velocity is positive. At point G, the acceleration, the displacement, the F net, they're all 0, and the velocity is positive. And then for point H, the velocity is positive, the displacement is positive, and the F net acceleration are negative. So just thinking through how the F net is opposite of the displacement, because right, if we have our spring, and this is positive, this is negative. If this is our equilibrium, right, when you go to the positive side, if this is your displacement, your force is going to point in the opposite direction. So just make that make sense, right? It's a restoring force. It's always going to point back to equilibrium. So, yeah, there you go. That's the first one. So now we can, I'll keep the graph here because it's going to be for page 2. But now we're just going to do problem 2. We have these four little carts with masses and springs. So if we had so let's just draw some scenarios. So if the amplitude was A, if you had an amplitude of A over 2, amplitude of A and amplitude of A, right? We have our springs. And we're just really ranking what is going to have the lowest and greatest sort of oscillation frequency. So let's just start the ranking. We have, if this is 2m, this is, and then the rest of these are m, and then these all have k, and then this is going to be k over 2. So so remember, frequency is different from period, because frequency is how often an oscillation happens. So just remember, frequency is going to be 1 over t, and this makes sense because it's one cycle, right? One cycle over a certain time, which is a period, and the period is how long it takes to take one cycle. So that's the equation for frequency. So if you have a big period, you have a low frequency, or a high period, low frequency. We know that, first of all, these two are for sure going to be equal. So A and B on your little thing, they're going to be equal because even though they have different amplitudes, we learned that amplitude does not affect period. They're going to have the same period. So we can for sure say these are going to be the same. So we'll call these like the baseline because they have K and M, right? This is the baseline one where they're equal. Really, for any of these, you don't have to worry about amplitude. When you're asked about frequency and period, you don't have to worry about amplitude. So for now these two, right, your K is now going to be half. So already you're going to have a lower frequency because T is equal to 2 pi square root m over K. So if your K lowers, right, if your spring constant lowers, your T is going to increase. So if your T increases, your frequency is going to be lower. Now, just remember that, make that kind of makes sense. If you have a lower spring constant, your spring is weaker, it's not going to be able to oscillate as fast. Same thing for mass. When you have double the mass, your mass increases, so your period is going to increase, your frequency is going to lower. In fact, these have the same period, right? Because if you think about T equals 2 pi m over k, if you make this k 1/2, right, that's the same as having T is equal to 2 pi square root 2m over k. Because this 1/2, right, the 2 comes into the numerator, it's the same T. In other words, really, the K and T, or the K and M, so your K and mass, they affect the T the same. So if you double the mass, it's the same as doing 1/2 the spring constant. So I would just say, right, so greatest would be A and B, which are equal. And then our least would be C, which is equal to D. That's how I would rank them. And yeah, hopefully that makes sense. So let me just check how much time I'm at. I have to do my phone the other way. Oh, 8 minutes, that's not bad. Let's go on to the next one. So we have to do, this one is not fun. We're basically are given these, there's an experiment, frictionless cart attached to this mass or whatever. When it's displaced from its rest position, it oscillates with the period T, 2 pi m over k. So you can refer to your graph for this one. I'm not going to draw all of it, but for A, right? So basically, in experiment A, it's going to have a period of T. And remember, T is equal to 2 pi square root m over k. So they give experiment A, the graph of experiment A. I'll just draw it. It's going to look something like this. And then we have experiment B, which looks something more like this. I didn't draw it the best, but this is A and this is B. Based off these graphs, so if this is time and position, what can we infer about what happened in experiment B, basically? So, the period is the same for both of these, right? If you were to see one full cycle, right, going front and then back and then where it started, front, back, or middle, front, back into where it started, it's the same time. So if K is the same, right, then M must also be the same. So what I'm trying to say is for A, the mass is, in experiment B, the mass is the same. So for B, the masses are equal, I'll say. And just think about it, right? If you have a graph like this, because this peak, so from the middle, this peak is greater. So what that just means is it has more of an amplitude. But we learned so more amplitude does not affect the period. So that's why they have the same exact period. For experiment C, so if you take a look at the graph for experiment C, and you can kind of, I'll try to show it here. So for this experiment, you can see this was the period originally, right? Sort of here-ish, yeah. But for experiment B, it's half of that. The period got halved. So if the period got halved, what happened to the mass? Well, we know the mass is going to decrease for sure, right? Less mass means more acceleration, so that's going to take less time to go the distance. But specifically, it's going to be 1/4 the mass. So for C, 1/4 the mass. Because, remember, it's proportional reasoning, really. T, I'll do it like this, T is going to equal 2 pi square root of some amount of mass over K. So if we want 1/2 T, remember, this is a square root. So you got to do 1/4 the mass. Because then you're going to get your, right, you're going to get your sort of 1/2 square root m over K, excuse me. Right, you're going to get the 1/2, and that's just proportional reasoning right there. Not much to really explain conceptually. Just understand that when mass lowers, your time is going to lower. Because less mass means more acceleration, because the force is the same. This was B, so yeah, whatever. This is A and this is B. But for C, it's going to ask us what's going to happen now if we double the mass and we double the spring constant. Well, let's think about this. I don't know why I erased that. I could have just used that. If we have T is equal to 2 pi the square root of m over K, we're doubling the mass, but we're also doubling the spring constant. So you can see mathematically they cancel out, right? So the period is the same. It's the original period. Doubling both things didn't affect anything. However, one thing to conceptually understand it, remember, it's really this idea of like when you double the mass, you're going to have more inertia. It's going to be harder to accelerate. But when you double the spring constant, so you write if F equals ma, F net is equal to, so the F, okay, I'll explain it like this. F net is equal to ma. So if you have more mass, you're going to have, you need more acceleration, but your F net is going to be negative kx. So if your mass increases, but your k also increases, right, your A is going to stay the same. So just thinking about that, right, more inertia, but you also get more force, so it kind of balances out there. Let's go on to the next one. All right, so this is where we're using this this graph again. So this is the last page, and I'll verbally explain this one. For the last page, it's gonna questions A through G. The first, and I'll kind of like go through. Which point? So for the first one, which points are the spring potential energy and the card's kinetic energy both at their maximum values? So I took that as like, when are they both at the maximum values at the same time? And the answer is none of them, because at point A it's all U spring, and then so at point A, I'm not saying this is the answer, but it's all U spring, and then to point C it transfers into K. So as U spring decreases, your K is going to increase. You can't have them both at a maximum, because when K is at a maximum, U spring is at a minimum. So just that conservation of energy idea. Which points is the kinetic energy equal to 0? So kinetic energy, right, 1/2 mv squared. When your speed is 0, you're going to have no kinetic energy. So it's points A and E. Because at A and E, right, there's that flat tangent line, your speed is 0, maximum compression, you have no kinetic energy. Now, what is the total energy at a maximum value? I mean, you could really say all the points, right? At every single point, they're at the maximum value, because there's no change in energy. There's no forces that do work on our system here for the Earth, mass spring Earth system. Okay, so at which point is the spring potential energy negative? This was a pretty, it's an interesting question. I would say none of the points. Because remember, let's think about it mathematically, right? U spring equals 1/2 kx squared. In order to be negative, spring constant's not negative. That doesn't make sense for it to be negative. So in order for U spring to be negative, this x squared would need to be negative. But that's impossible because when x is negative, you're squaring it. When you square a negative, you're just going to get a positive. So just mathematically, it's impossible to have negative U spring just in this, with this scenario. But also, U spring is caused by stretching or compression, right? So even when you have stretching or compression, which is literally the entire time, you're going to have U spring. The only time it's not stretched is when there is no stretch at all. Wait, that was redundant. C and G, right? That's when its U spring is 0, but it's never going to be negative. So negative displacement does not mean negative energy. Which points are the kinetic energy positive? Same idea. All are going to be positive. It's always going to be positive because of that K is equal to 1/2 m v squared. So when you have a negative v, same idea, you're squaring it, your kinetic energy is going to be positive. And kinetic energy is just energy in movement. So whenever you're moving, no matter what the direction is, you have kinetic energy. It's not going to be negative. Except, obviously, when you're not moving, you don't have kinetic energy. When is kinetic energy at its maximum? And then when is U spring at its minimum? I would say C and G. Because at C and G, they're not compressed. So there's no stretch. U spring is equal to 0. So conservation of energy, if U spring is equal to 0, then K is at its maximum. Same idea for the last one here. When is kinetic energy at a minimum? When is potential energy at a maximum? When the speed is 0. So at A and E. Because when the speed is 0, you have no kinetic energy, so it has to be stored all as K. So yeah, sorry if this is a bit of a longer video. It's a bit of a longer worksheet, to just be honest with you. But yeah, let me know if you have questions. Hopefully this wasn't terrible. It's just really energy stuff. So yeah, thank you for watching. Bro, oh my god, it didn't stop.